Am I audible to all?
Yes, sir.
Okay. A very good afternoon to one and all. Today we'll be starting a new unit, unit number 4. So, what does this unit number 4 comprises of? What we are going to learn or what we are going to see in this unit, I'll highlight you first. Okay. So, let's start for today's session. Yeah, unit 1 is cyclic codes. The other three units, unit 1, 2, and 3. Unit 1 to 3 is a slightly different concept while compared to cyclic codes. So first I'll illustrate you or give you highlights as what is there in cyclic codes as per your syllabus. The description of cyclic codes, generator of parity and check matrices of cyclic codes, encoding, cyclic Hamming, syndrome computation, error detection, decoding of the cyclic codes, decoding of Hamming cyclic codes, error trapping, improved error trapping. After that, we have a specific n comma k, 23 comma 12 Gole codes, shortened cyclic codes, cyclic product codes, and quasi-cyclic codes. So these are the contents of unit number 4. But before starting all this description of cyclic codes and all, we need to be familiar with some of the concepts which is out of your syllabus. Okay, so that we are going to see in this class. What is the purpose of the cyclic codes? How it is being originated? What are the prerequisites? What are the basics? And all you are going to see, which is or which will be discussed in this session. Okay, so it starts from channel encoding. I think most of you are familiar with the block diagram of communication system, which consists of a transmitter, a receiver, and in between transmitter and receiver we have a channel in between. Our messages will be sent in sequence of datas which has to be encoded by using an appropriate encoder and decoded at the receiver by using an appropriate decoder. So that the process of converting this data sequences into an appropriate bits of information can be done by sampling theorem, and the procedure we call it as coding. Since we are going to deal with the channels where more amount of noise is present or where errors occur, so that has to be minimized. So analysis of the channel coding is a very big task. So first we'll see what is this channel coding is. Then we'll see a type of that as your cyclic codes and convolutional codes. So channel coding is something that adding an extra bit of information to the input message. This is the function of a channel encoder, adding some extra bits of information to the input message. Then that encode messages will be transmitted over the channel, either AWGN or noisy or relay or fading, Nakagami, whatever might be a channel. It will be transferred over that. Then in the receiver section, the channel decoder will identify the extra bits, and that extra bits, which we called as redundant bits, are used to detect and correct the errors in the obtained message signal if there is any errors. If there is any error being occurred due to the noisy channel or due to the environmental conditions, all they will be detected first, then corrected. So first let us see, there are two different types of channel coding. One is waveform coding, another one structured sequences. So in the waveform coding is subdivided again into orthogonal codes and bi-orthogonal codes, whereas this structured sequence is divided into three. One is block codes, second one conventional codes, third one turbo codes. Let us see what are this in detail. And you will be asking me a question, where does this cyclic codes comes? So you had said that cyclic codes is unit number 4, but where is cyclic codes? So cyclic codes is a type of block codes. Under block codes we get linear block codes and the cyclic codes. So a type of that is present in that. So in order to realize this cyclic codes, first we should be familiar with block codes. Okay. First we'll see types of error control. What is the mechanism being used in error controlling? How to control it in two different mechanisms. An error is occurred, how do we rectify it, or how do we minimize the error? It can be done by two different mechanisms. One is forward acting error correction, in which the errors are detected and corrected by proper coding techniques at the receiver with the help of a decoder. The check bits or the redundant bits are used by the receiver to detect and correct errors, where the error detection correction capability of the receiver will depend upon the number of the redundant bits, which is our extra number of bits added with the input message. This method is faster, but the occurrence of errors, probability of occurring of errors is always higher. So this cannot be used as a technique for correction at all, because still as we do it at a higher or a faster rate, the probability of error will be higher. So this mechanism, this type of error control can be a problem which is to be addressed. So second method or second type of error control mechanism is error detection with retransmission. Error detection with retransmission. In this method, the decoder checks the input sequence at your receiver. When there is any error, it discards that part of the sequence. If there is any error detected in that input sequence, so that particular sequence is being discarded or removed off or deleted. And it requests the transmitter for retransmission. It will send a signal to the transmitter, resend this sequence of data, there is an error. So what the transmitter will do is that the transmitter will again retransmit that part of the sequence in which error was detected. And if there is no error, it will detect and transmit to the receiver. And again, if there is an error, it will ask again to retransmit. And the next time, if there is no error, it will directly send it to the receiver. And if there is an error, again it will go. Okay, till we obtain the desired input sequence without any errors. Till that, it will do the same. So the concept is that it will just detect the errors and send requests to transmitter. So by this way, we will get lower probability of error, but the received signals will be receiving at a slower rate. So these are the two mechanisms. One is faster but high probability of error. Second one slower but probability of error is very low in these two mechanisms. So what are the errors being introduced? We had said about error controlling. What type of errors can be controlled? Is that there are two types of errors that occurs during the transmission of a data. One is random error, second one burst error. So what is this random error? Is that the random errors are obtained due to white Gaussian noise, as I said earlier, white Gaussian noise which is present in the channel, and the errors generated due to this will not affect the performance of the system in subsequent intervals. In other words, you can say that these type of errors are uncorrelated. In the sense, though the errors are occurring, these may have not much impact on the overall performance of the system. So this is your random error occurring randomly in nature. Second is that burst errors. These burst errors are due to impulsive noise in the channel. These are generated due to the circuits, lightning or switching transients in the circuit, which may make the symbols to become as noise. A successive set of sequence of symbols will be passing through. So due to the lightning or switching transients of the circuit, these symbols will turn into noisy circuits called as burst. So this type of errors that are being occurred due to impulsive noise is called as burst errors. And these are dependent on each other. If one is affected, the next subsequence also will be affected. So they are dependent on each other. Next, some of the important terms that we should know before starting the cyclic codes is code word. I think we had discussed already code word. What is code word? How to obtain a code word we had seen, but the actual definition of code word I haven't told you. Okay, so code word is the encoded block of n number of bits that consists of message bits and redundant bits. Message bits is your information data sequences which has some input bits which you call as message bits, and redundant bits are the checksum bits or the parity bits that we are adding to the transmitted signal, or the redundant bits are the extra information that are used to check the errors at your receiver. So combination of those two we call it as code word, which is represented as n bits. Okay. Next is block length. Length of the block. Length of the block is for a particular code word, how many number of bits are present. How many number of bits are present? Number of bits present in the encoded block is called as block length. Next terminology is code rate. Code rate is the ratio between the message bits k and the encoder output bits n. For example, we had represented the code word length as n and we have messages k. So the code rate will be always the ratio between the message bits or your information bits k to the encoder output bits n. So R will be your code rate. So R is equal to k by n. And we can say that always the code rate will be varying from 0 to 1. 0 to 1. This is your third terminology. Next, fourth terminology is channel data rate. This is the bit rate at the output of the encoder. Keep in mind it is output of the encoder. If the bit rate at the input of the encoder is RS, okay, we have an encoder. We are going to consider the input of the encoder and output of the encoder. So take the number of bit rate at the input of the encoder as RS and the output of an encoder. Then the channel data rate will be N by K RS. So N is the number of encoder output bits into input of encoder bit rate of input of encoder is RS divided by message bits. So channel rate can be given as N into RS divided by K. Output of the encoder into bitrate of input encoder divided by total number of message bits. That gives your channel data rate. So these are the four terminologies. Next terminology is code vector. Code word is different, code vector is different. So an n-bit code word can be visualized in an n-dimensional space. For example, if you are having a 3-bit code word, so it can be represented in 3-dimensional space. If you are having 4-bit code word, it can be represented in 4-dimensional space. So here I have taken 3-bit. So let us see how this diagram is being drawn. So if you have 3-bit code words, so then the number of code words will be 2 power k, which is 2 power 3 is equal to 8. So how do we write this 8 is that we'll be having B0, B1, B2. So B0 can be drawn on x-axis, B1 can be drawn on y-axis, B2 can be drawn on z-axis. So this 2 power 3 will give us 8 code words, which is 3-bit code word. Will give 8 code words. So 2 power 3 is 8 right from 000, 001, 010, 011, 100, 101, 110, 111. So these are the code vectors. So these code vectors can be drawn in this 3-dimensional space. I think this diagram we have drawn in unit 3, I think so. A small diagram on representing 2 power 3 I had drawn. The same diagram is this. Draw the coordinates of x, y, z, point each and every one. 0, 0, 0, 0 will be here. In x we have 1, in y we have 0, in z we have 0. Like this. You can plot all these values. This is the 3-dimensional space representation of 3-bit code word. I'll keep this slide for 1 or 2 minutes such that you can analyze each and every one. X, Y, Z of 001. Here 101 is written here. How do we get 011? How do we get 010? How do we get 111? How do we get 110? 100, 000, representing in XYZ axis. Okay, then we'll go for the next terminology, which is Hamming distance. So how to calculate this Hamming distance? We had seen Hamming codes in unit 3, but we didn't see Hamming distance. So how do you determine this Hamming distance, which is a major property in cyclic codes, is that the Hamming distance between two code vectors is that the number of elements in which these two code vectors differ is called as Hamming distance. For example, you have code vectors here. I have serial number one code vector, some vector, this is some vector, this is some vector, this is some vector, this is some vector, some vectors are there. So take any two vectors out of this and see in how many bits they differ. For example, I take for 1 and 2, 0, 0, 0, 0, 0, 1. Compare this and see how many bits are being differed. In these two, when I compare in z-axis, 0, 0 is same. In y-axis, 0, 0 is same. In x-axis, 0 is here, 1 is here. So 1 bit change. So the Hamming distance will be 1 for that 2. Now I take, for example, 101 and 110. Compare these two. 101, I'll take, okay, 101 here. This is 101 and I see 110. So compare these two on a z-axis. When I compare, z-axis is same but y-axis differs. So one distance. So x-axis also differs. So 2. So the Hamming distance for between code vectors 101 and 110 is 2. So I can write the Hamming distance between x and y as given in this example as 2. So this is how to find the Hamming distance. And I'll give you an question in the chat box. Is it audible now? I'll give you a question in the chat box. You find and tell me what is the, yeah, okay. You find and tell me what is the Hamming distance between them. Yeah, can anyone give the answer for this question in the chat box? Q value is given, R value is given. Yes, 2 is the answer. Now I'll give you another option. Yeah, I posted you another question. Yeah. Very good, Vishnu, Shrikala, Kishore, Pavan Chandra. Yeah. So 3 is the answer. So for a 3 bit, I'll go back to the PowerPoint. Yeah. When you see this 3-bit code word, there are 8 combinations. Okay. So what is the maximum Hamming distance for this 3-bit code word? For example, when you compare 1 and 2, there are 2 changes. When you compare 2 and 3, serial number 2 and 3, you get 2-bit changes, and you compare with each and every one. What we get is that when we compare, let me show you. When we compare each and every bit with the other bit sequences, the maximum Hamming distance is 3. Yeah, as Kishore said, yeah, it is 3. So for a 3-bit code word, the maximum Hamming distance is 3. I'll show you that. Thus, we can observe that the Hamming distance between any will be maximum of 3 only. You can refer that diagram also, or we can obtain it from the table. Okay. So understood the maximum Hamming distance. So next, we are going to see about minimum distance. Minimum distance, d minimum. So this is the smallest Hamming distance between valid code vectors. Minimum distance between valid code vectors. In general, we are going to write. Okay. So if an error is being occurred, then the received vector will not be equal to the code vector. If error is occurred, received vector will not be equal to the code vector. So then this illustrates that the transmission errors in the received code vector should be less than minimum distance. It should be less than the minimum distance. So in order to have the minimum distance, the error control capabilities should satisfy this distance requirements. That is that if you want to detect up to yes errors per word, up to yes errors per word, then the distance should be greater than or equal to s plus 1. This s plus 1. S is your syndrome. That also will define in subsequent classes, don't worry. And if we want to correct the errors, we can correct up to t errors per word depending upon 2t plus 1. Detection is s plus 1, correction is 2t plus 1. And if you want to correct up to t errors and detect beyond s greater than t errors per word, then the minimum distance should be greater than or equal to t plus s plus 1. If these three are being satisfied, we can easily remove the errors from our transmission system or from the communication. Okay, so this is what minimum distance is. Minimum distance required for detecting up to s errors is s plus 1. For example, if I have 2 errors, so minimum distance is 2 plus 1, which is 3. If I want to correct t errors, for example, I have 2 errors, the minimum distance per word should be 2t plus 1. So 2 into 2, 4, 4 plus 1, 5. And if I want to correct and detect if errors are greater than s greater than t. So then d minimum should be t plus s plus 1. This is how to error control the channel. We'll see in a problem, don't worry. When you solve a problem based on this, you'll be getting a good idea. So next important terminology is code efficiency. We had seen code rate. Next is code efficiency. The code efficiency So the code efficiency is that number of messages bits in a block. Let me check for audio. Number of yeah, number of message bits in a block to the transmitted bits for that particular block, which we call it as code efficiency. So if we have an n comma k block codes, because we are taking a set of code words or we are taking a set of code vectors, so which we call it as block codes. So if there are k message bits and n transmitted bits, so n transmitted bits consists of the message bits k as well as the check bits q. Okay, so n will be always q plus k or k plus q. So then the code efficiency can be given as k by n. So this is equivalent to your code rate also. So code rate and code efficiency will be same. Next is that you need to define weight of the code. Weight of a code. So how do we find weight of a code is that, for example, an x is given x 0 1 1 1 0 1 0 1. So out of this we should find the number of non-zero elements. So you can see that how many non-zero elements are there? 1, 2, 3, 4, 5. So the weight of the code is 5. So the number of non-zero elements in the transmitted code vector is called as vector weight. In some cases, we may write in terms of R array. So it may a chance that we'll be writing 0, 1, 2 in sequences also. Okay. Or we can state that for this particular example, counting the number of ones. So how many number of ones is there? 1, 2, 3, 4, 5. So the weight of this code is 5. So this is how to find weight of each code. So next, let me give you an in chat box. I'll give you an question. So try to find the weight of the code. Can anyone answer the weight of the code? Okay, 3. Now I'll give you another question. Okay, anybody answer? Anybody else also can check and answer? Okay, right. Three. Very good, Pavan Chandra. Very good, Sri Vishnu. Very good, Srija. Yes, correct, Tanuja. Yes, Shrikara, it's correct. Three is correct. Now, the weight of this code is 4. The thing is that the number of non-zero elements you should count it. Correct, Shrikara. Correct, Pavan Chandra. Sri Vishnu, it's not 6. It is 4. Srija is correct. Shrikala is correct. Pavan Chandra is correct. Okay. First he had given 4, then he had given 6. No, Vishnu, it is only 4. See the number of non-zero elements. Totally we are having b is equal to 0, 1, 2, 1, 2, 0. So total length of the code word is 6, whereas weight of that code is only 4 because there are two zeros. In order to calculate the weight of the code, we should take only the number of non-zero elements. Understood? Yes, Tanuja. You can type in chat box. So the representation of 0, 1, 2, 2, 1, 0 in quotes, the number will be there as, okay, that's what, 0, 1, 2, 2, 1, 0, which I wrote. It is in the case of R array. R array. If you take R array codes, this is how to determine weight of the code. In binary, zeros and ones. If my R value is 3, so I had given an example of R is equal to 3. That's what we had discussed in R array. In R array codes, if R is equal to 3. In R array codes, if R is equal to 3, so 3 representations 0, 1, 2. Now got the point? Yeah. Okay, thank you for all the correct answers. Then we'll proceed for the next topic, which is structured sequences. The structured sequences are classified into three parts. One is parity coding, second one block coding, third one convolutional coding. So in our unit 4 and 5, in unit 4 we are going to see a type of block codes which we call as cyclic codes, which comes under this block codes. In unit 5 we'll be completely seeing the convolutional codes. Okay, so this is where we are going to see, right? So before seeing that, we will be seeing parity coding. So what is this parity coding? Is that adding messages to the adding the redundant bits, adding the redundant bits to the message bits. We call it as parity coding. So what type of parity we are going to add is that we are going to add it as odd parity or even parity. So this odd parity or even parity will act as our error detection and error correction also. Okay, so parity bits are added to the message, either odd or even at the time of transmission, and depending upon the odd parity or even parity, receiver will detect errors, which is the first structured sequence. Second is that the codes, which consists of n number of bits in one block or in code word, will have k message bits. Will have k message bits and q redundant bits. So which is n minus k. Code word having k message bits and some redundant bits are added, which are n minus k, or you can say it as checksum bits. Q is equal to n minus k. So that type of codes structured in sequence we call it as block codes. The third type is that the coding operation of the code sequences are being done with discrete time convolution. We'll be doing convolution of the input sequences with the impulse sequences. I think most probably you would have studied this convolution in signals and system, and you'll be studying in DSP also, digital signal processing. So that convolution procedure is being used for generating and encoding sequences. What does this convolution will do is that the input sequence and the impulse sequence will be convolutionally performed by using modulo 2 operation. Mostly we'll be using modulo 2 operation depending upon the input bits, and depending upon the impulse bits, we'll be doing some modulo 2 addition. So then the resulting codes we call it as convolutional codes. So then that will be sent through the convolutional encoder that will accept message bits and generate encoded sequences continuously. So these are the three type of structured sequences. Then this structured sequences can be further classified into two forms. One is linear codes, another one is non-linear codes. So what is this linear code? Linear code is that if two code vectors of linear code are added by modulo 2 addition, then it produces a third code vector in the code. If two code vectors, if they are added by using modulo 2 addition, then it will produce another third code vector, which we call it as linear codes. If you do the same type of addition of the non-linear code, so then it is not necessary that it will produce a third code vector, third code word. So this we call it as non-linearity. Linear code words, non-linear code words. If two code words are taken, if they are done modulo 2 addition and it produces a third one, third code word in the code, we call it as linear. If it doesn't produces, or there is no necessity that it should produce a code word, is called as non-linear. So in our unit 4, all we are going to see is a linear code word, which we call it as linear code words of blocking type. Linear code words of blocking type. So we'll see this. What is this linear code words? So before that, we'll see how do we get a block coder. Let me check for any queries till now in the chat box. Then I'll proceed for this block coding. So next topic is block coding. This diagram represents the functional block diagram of block coders. So far I had said about block codes, right? So block codes consists of n number of bits in one block or in one code word, which will have k number of message bits and n minus k redundant bits. So that I'm going to show you. So this is. So we have message bits of sequences k bits. So k bits, this is given as your input to the channel encoder. So this will give an output. So how it will give as an output is that it will give in terms of n. Message input is k, code encoder block output is n. So what is present in this n is that message bits of k plus check bits n minus k. So this is your entire block diagram. So what is present, I'll show you in the next. So when a channel encoder is used, the message bits which are being transmitted are being added with the check bits of having n minus k. So this type of codes which are having n comma k is called as block codes. And in a systematic block code, the message bits appear at the beginning. You can see here it appears at the beginning of the code word, and the check bits will be added at the end of the code word. Okay, you can see that message bits appear first and check bits are transmitted in a block. So this type of code is called as systematic code. Systematic code. Message bits first, check bits second. And in some type of codes, what happens is that inside the message bits itself, check bits will be present in between or in a mixed format, which we call it as non-systematic code. So it is highly impossible to identify which bits are message bits, which bits are check bits in non-systematic code. Okay, because they'll be mixed together in the block, so which are very difficult to identify since all will be in terms of binary zeros and ones. If you transmit an binary, okay, so it is very difficult. So we'll be seeing about the systematic block codes. So now coming to the definition of linear code. Linear codes are that the sum of any two code vectors produces another code vector. Then that any code vector can be represented as a linear combination of the other code vectors. If this occurs, this we call it as a linear code. As we had seen, definition, linear code. Two code words of linear code are added by modular addition. Then it produces third code in the code. So which is yes, so linear code. So we'll see the definition of that. Consider a particular code vector consists of messages m1, m2, m3 till mk, message bits c1, c2, c3 till cq, check bits. Then the code vector can be written as x, which is your message, is equal to message bits and check bits, where as I said earlier n minus k is your q. So q is your redundant bits being added by the encoder, which is represented by the number of bits n minus k. N is the number of bits of message, k is the number of bits of n is the sorry, I forgot. K is the number of message bits, where n is the total number of bits in that code word. Okay. So I can write x is equal to m and c. M is to c. So k bit message vector and q bit check vector, which is represented as capital M message and a capital C check bits respectively. Then what is this? What is the role of this check bits? We are going to see. So this check bits always plays the role of error detection and correction. And the role of this linear code is to generate those check bits correctly. Generating this check bits correctly. Then how do we generate these check bits correctly is that x is equal to this x is equal to m into g. So where g is the generator matrix of size k cross n, x is the code vector of 1 cross n size or n bits, m is the message vector of 1 cross k size or k bits. Because m is this, so k bits, message k. And the size of this generator matrix, which is being obtained for your check bits, is always in the size of k cross n. So hence we can write this equation in terms of matrices also, which are very easiest in solving, as x, which is your code word or the code vector, is equal to mg. So the matrix representation of the number of rows and columns in x will be 1 cross n, because our code vector will be having bits up to n, so 1 cross n, and message will have bits from 1 to k, so 1 to k, and generator matrix will have the size k cross n. So this is your matrix representation of linear codes. So this type of linear codes that is used for error detection and correction using blocking principle, we call it as linear block codes. Linear block codes. So this is what we are going to see in linear blocks. We'll see with an example also how to generate this G, how to generate M, how to generate X, how to find error of this linear block codes easily. It is the same procedure with some difference in cyclic codes. Why? Because cyclic codes is obtained from your block codes. So this is your representation of generator matrix. As I said now, generator matrix G k cross n. How do we get that? So this generator matrix depends upon the linear block code being used, and it is represented as IK, identity matrix, and P, which is your submatrix of your generator matrix. The identity matrix will be obtained by the number of message bits. I think everyone are familiar with identity matrix writing. So if there are 3, all the diagonals will be having 1 1 1, remaining all will be 0. So that is identity matrix. All are familiar with identity matrix. So P is your submatrix, which is used for generating your check vector. So the check bits can be generated by C is equal to MP. You can see that C here. C can be this C equation. C check bits. So the purpose of linear block code is to generate this check bits. So how do we generate these check bits? Is that it depends upon M and P. So now let us expand this in matrix. C is equal to MP. So C will be having till 1 cross Q, C1, C2 till CQ, and message M1, M2 till MK, 1 cross K, and parity matrix P. So P11, P12 till P1Q, P21, P22 till P2Q, PK1, PK2 till PKQ of matrix K cross Q. Since K is your number of message bits, so depending upon the number of message bits, we have to write the P bits, which is your parity. Okay. Next, then how do we obtain this C1, C2, C3 till CQ is by modulo addition. For example, if I want to find C1, this M1, M2, M3, M4 till MK should be multiplied with the first column. This row with this first column for obtaining C1. And this for C2, this row with second column. C3, this message bits row with third column. So what we are going to do is that we are going to do modulo addition of them. So M1, P11, always we do plus or addition in the case of normal matrix manipulation, but here we should do modulo 2 addition. So M1, P11, modulo 2 addition of M2, P21, modulo addition of M3, P31, modulo addition of M4, P31 till the modulo addition of MK, PK1. Then similarly for C2, M1, P12, modulo addition of M2, P22, modulo addition of M3, P32 till MK, PK2, and it goes on till CQ obtaining till we get CQ. So we'll see this with a problem. Need not worry. So any doubts till this? Because with this basics, we'll be solving a problem. So with this basics of linear block codes, I'll show you a problem solving as how to find code vectors. So the given question is a generator matrix for a 6,3 block code is given below. We have an generator matrix which is G for a 6,3. So if you write 6,3 here, it represents that this value of 6 is equal to n. I can show you that here. It is a 6,3 matrix. It is always n, k block code. So you can see here n is 6 and it is an n, k. So n, k is 6,3. So n is 6, k is equal to 3. Okay. So we can find easily n, k also. So n, k will become obviously 3, which is q. So q is always 3 here. You can find it easily. So you can see that there are 3. Okay. So This 100 is to 011, 010 is to 101, 001 is to 110. Okay, so this is your identity matrix. Just now I had said, which I'm highlighting here. This first 3 cross 3 matrix is your identity matrix. Okay, so the remaining whichever is given is your P matrix, P submatrix. So this is how to differentiate or identify. Okay, so for this we need to find code vectors. So how do we find code vectors? So for that, the following 3 steps has to be done clearly. I want to find code vector. How do I find code vector? Is that first I should find P matrix. If P submatrix is found, we can easily find C. And if C is found, we can easily find X. Why? Because our formula is this. The question is given to find code vector. So code vector is written as X is equal to MC. Okay. So where M is the message bits and C is the check bits. How do you find check bits? Is that C can be found out by generating the check bits. So how do you find C? C is equal to MP. So how do you find P? P is from the given submatrix of G. So this is how to find. Okay. So now let us see. So determine P submatrix from generator matrix. So this is your P. Obtain equations for check matrix using C is equal to MP. Determine check bits for every message vector. We will get the code vectors. Now first let us find the P submatrix. So this is your P submatrix. Okay. So generator matrix is written in the form of IK is to PK cross Q. So we can easily find identity matrix. Q is 3, so 3 cross 3. Sorry, K, not 3. K is 3 obtained. So I 3 cross 3 is 100, 010, 001. So this is your matrix for that, IK matrix. Then the remaining is your P matrix. So P matrix is 011, 101, 110. So write it as it is. So first we had found P. Next we need to find check bits. How to find this check bits? Now determine n value, write the n value, write the k value. So n minus k is q. Okay, so n minus k is 6 minus 3, which is 3. Hence we get k is equal to 3, q is equal to 3, and n is equal to 3. So now see how many message bits are there, message vectors are there. We have 3 message vectors. So 2 power 3 is 8. So 2 power 3 is 8. So we can write the combinations in this m1, m2, m3 like this in this format. Okay. 00, 001, 010, 011, 100, 101, 110, 111. Right from 000 to 4, 3 ones. Why? Because this is the 3-bit message vector. So 3-bit message vector will generate 8-bit code vectors. So write that. Then parity matrix you can write as it is, which you had obtained here. So write it. Then we need to find what P is found, M is written. Then we need to find C. So C is equal to MP. So C, since we are having only 3 check bits, so C1, C2, C3 is equal to M1, M2, M3 into parity. So parity is this 011, 101, 110. Now do matrix manipulation or do m1 into this modulo addition of m2 into this modulo addition of m3 into this will give you c1. And for obtaining c2, m1 into this 1, m2 into this 0, m3 into this 1, we get c2. Then how do you get c3 is that m1 into this one, m2 into this one, m3 into this one, and do modulo addition of them. So when you do that, for c1 I will get m2 modulo addition m3. Answer will be. And if for c2 I will get m1 modulo 2 addition m3. For c3 I will get m1 modulo 2 addition of m2. So let us check that. Yes, here it is. So we'll be getting three equations: C1, C2, C3. C1, C2, C3. A simple matrix multiplication. Then the real code vectors determination is to be done. How do we find the code vectors? Is that tabulate the message bits. See this table 3.3.1. Tabulate this. So write this message bits of vector in one block. 000, 001, 011, sorry, 010, 011, 100, 101, 110, 3 ones. Write it here, M1, M2, M3, write it as it is. Next, write the check bits. Check bits are C1, C2, C3. So C1 is M2, M3. M2 modulo 2 addition M3. C2 is M1 modulo 2 addition M3. Right, it is. C3 modulo 2 addition of M1, M2. Right, as it is. So this is your message bits. This is your check bits. Okay. Now what you do is that perform this C1. What is C1? M2, M3. What is M2? 0. M3, 0. So do modulo 2 addition as it is done in the for first block. For example, C1 is message is M1, M2, M3, 000. C1 can be computed by 0 modulo 2 addition 0, which is 0. Similarly, C2 can be found M2 and M3, 0, 0, 0, you get 0. C3, 0, 0. So C1, C2, C3 will be 3 zeros for first block. So what is this modulo addition I had written in pen? XOR operation 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1 is 0. That is what your modulo 2 addition is. Similarly, do it for next block 0, 0, 1. So 0, 0, 1, when we take C1 is M2, M3. So M2, M3 is 0, 1, you get 1. So C2 is M1, M3. M1 is 0, M3 is 1, so you get 1. C3 is M1, M2. M1, M2 is 0. So if both are 0, it will be 0. So check bits will be 1, 1, 0. Do it for third block, fourth block, fifth block, sixth block, seventh block, eighth block. Tabulate C1, C2, C3 as like this in check bits. Till now only the check bits. C1, C2, C3 for different M1, M2, M3 in each blocks. You need to find. If you find, you will get this check bits. So check this. Surely you will get these values. So after completing this, kindly check, you will get these values. After completing this, my question is to find all code vectors of this code. So what is code vectors? Code vectors are this: X, X is your code vector with combination of M message and C check bits. So we can write the combination of this. This is your complete code vector M and C for that particular code word. So if my code word of M1, M2, M3 is 3 zeros, the complete code vector will be combination of M1, M2, M3 with C1, C2, C3. So if there are 3 zeros of M1, M2, M3 and 3 zeros of C1, C2, C3, the complete code vector for this message block is 0, 0, 0, 0, 0, 0, 0. So this is your complete code vector for first sequence, first block. Similarly for second block, what you have found, write it in completely together. Third block, M1, M2, M3, C1, C2, C3. So write as it is. For fourth block, M1, M2, M3, C1, C2, C3, and it goes until all the blocks. So this is how to determine the complete code vector with a problem. So any doubts in this? I'll leave this slide for 2 or 3 minutes. You can check this code vectors determination for a specific example of 6,3 block code. Because the same procedure will be using it for cyclic codes also. If you learn block codes, then cyclic codes also will be easier. So let me check in the chat box and I'll be back with this slide. Everyone try to have an take a paper, note down this M1, M2, M3, parallelly do this C1, C2, C3, and check whether you're getting these codes. Class. Class. Upper class. You can check this is how to find code vectors. For this specific n comma k block codes having 6,3 values of n and k respectively. I'll go back for a glance so that you can easily see. Generator matrix is given. Generator matrix is given. N comma k block codes. N is 6, k is 3. We need to determine code vectors for each. First determine the P matrix, P submatrix. From P submatrix find check bits. C. If C is obtained by using MP, C is equal to MP, then we can determine the code vectors very easily. The concept is that we need to use modulo 2 addition, which is XOR gate operation. When you had studied your digital electronics, you would have asked your sir or madam, sir, what is the use of this and all. Now, see, this is where we use the XOR operations. Okay, I think, let me check the time. Okay. So next we have, I think, parity checking, parity check matrix, Hamming, and a problem based on that. Okay, still we have more decoding. All these things we'll see in next class. So till now, we were at computer. I'll make a note such that the continuity doesn't miss us in next class. Parity check. Okay. Kindly await. I'll send you the Google form for attendance. In the chat box, you can see the attendance link is being posted. If you had filled the attendance, you can leave. Fill the Google form attendance. Vamsi is there. Vamsi C009.
Yes, sir.
Why yesterday absent?
Sir, health is not good, sir.
Take care of your health.
Okay.
And what about Vamsi? What about Pavan Kalyan Reddy?
Sir, is not in contact, sir.
Okay, where is his hometown?
His hometown is near Guntur, sir.
Whether he is attending other classes?
No, sir, not attending any classes.
Okay.
He's
Has he
having.
informed? Has he informed to class in charge?
I don't know, sir. I will ask to CR.
Okay, Sai Ganesha.
Yes, sir.
Okay, okay. If you had filled the form, you can leave. In next class, we'll discuss.
Okay, sir.
Okay, Raj. Thank you.